Hi, welcome to Work Energy Power Assignment 2. All right, before I move on, please remind yourself that if you do not have to watch the entire tutorial, okay, you just skip, look at the description of the in the YouTube video, and then skip to the question that you need help in. All right, there is no need for you to go through the entire solution video. All right, but if you do go through, I appreciate your dedication and your self-directedness as well. Okay, same thing, tutorial, the definition question, I will not focus too much on it. State what is meant by work done, refer to the notes. SI unit for work done is the same as the SI unit for energy. So in this case, it's Joule, symbol big J, okay? A 15 Newton force pulls a 2.0 Newton mass, all right, from rest to the top of a ram as shown. Okay, so calculate the work done by the 15 Newton force on a 2 kg mass. All right, work done. What is the formula? Force times what? Very similar to the one in moment, right? Force times distance. All right, the difference is moment. We are talking about perpendicular distance, okay, between the applied force and the pivot. Okay, whereas for this, we're talking about the distance moved in the direction of the force. Okay, moved in the direction of the force. So in this case, the direction of the force is 15. Where is the direction? Where is the distance in the direction of the force? Are we talking about 8? Are we talking about 6? Of course not. We are talking about 10, right? 150 joule. Okay, very straightforward question. So B, they say if the frictional force acting against the 2 kg mass is 10 Newton, what is the work done against friction? Okay, so I think this is a relatively new term, and definitely you're not going to see this one time. You're going to see this very often. Work done against friction basically means the energy that is lost in the form of thermal and sound energy when you push against friction. And of course, when there is friction. So in this case, they're telling you that the friction is 10 Newton. Oops, the friction is 10 Newton. Right? So where is this 10 Newton acting on? The entire distance when the box is moving up in the opposite direction, right? So in order to overcome that, okay, energy is lost, right? So what is the energy, or rather the work done against the friction? So work done against friction will be frictional force. Same, the formula is the same, but the F is not just it's not your applied force, but it's the friction that we're talking about. Okay, the frictional force multiplied by the distance where the friction applies, which in this case is the 10 Newton, right? So it's 10 times 10, 100 joule, right? So I want you all to take some time to internalize this. I did 150 joule of work. 100 joule of work is worked against friction. Okay, so what is the gain in GPE by the 2 kg mass? Okay, what is the gain in GPE by the 2 kg mass? So let's try. Okay, change in GPE equals to mgh, right? We talked about that in the previous assignment. So 2.0 multiplied by 10. What is the gain in height? 6 meters, right? We're not talking about 10 meters anymore. 10 meters is not the height, all right? It's an inclined distance. Okay, so we're talking about the 6 meters. So what is it? 120 joule. Okay, all right. 3. A boy exerts a force of 150 Newton to push a trolley from A to B as shown in the diagram below. Calculate the work done by the boy when the trolley moves from A to B. Okay, work done by the boy. Very straightforward also, right? Work done equals to force times the distance moved in the direction of the force. Exerts a force of 150 Newton. Distance moved is A to B is 16 meters. So again, a very straightforward question. Okay, 150 multiplied by 16, 2,400 joule. Okay. If the boy now pushes the box up the slope from B to C, okay, with a work done of 400 joule. So what is the force exerted by the boy? So now in this case, we are still going to use the same formula, right? But they give you work done, they give you the distance, which is 8 meters. They want you to find F. So can we find F? Of course we can. All right, W over D. 400 joules divided by distance 8. So this is 50 Newton. So The boy actually exerted a force of 15 Newton up the slope. Okay. Question 4. A force of 12 Newton pulls a block of concrete over a distance 3 meters along a level floor. Level floor means it's horizontal. There is no gain in height, hence no work is done against gravity. Alright, means there's no gain in GPE. The block weighs 8 Newton. So the frictional force acting against the block is 5 Newton. So calculate the work done by the 12 Newton force. So they already told you, right, what is the work done by the 12 Newton force. So I'm just going to calculate according to the 12 Newton force. I'm going to ignore the 5, which is the friction. I'm going to ignore the 8, which is the weight. So work done equals to force times distance, 12 times, what's the distance moved? 3, 36 Newton. Sorry, Joule. All right. I understand that, in an assignment, it seems like, we keep repeating the formula, all right, but because this is assignment, all right, repeating the formula because every single question is on the same topic. But in exam, you do not have this kind of luxury, okay? So I want you all to make sure that every single question, if there is a formula attached to it, write down the formula, all right? It may earn you the mark. State the work done by the 8 Newton weight as the concrete moves 3 meters. Okay, so this is actually, okay, I'm going to explain this question in two ways. One is explain it in terms of course, concept, all right? The weight is acting vertically down. The distance moved is actually horizontal. According to the definition of work done, it is the product of the force and the distance moved in the direction of the force. The direction of the force in this case is vertical. Did the box drop? No. Since the box did not drop, it means that technically speaking, the distance moved in the direction of the force is 0. So work done equals to force times 0. Therefore, 0. Okay, this is understanding the question in a very conceptual approach. Another way to look at it is, one thing is, you see, they will use the word state, right? So in physics, or rather in exam, sometimes, it is important to understand the question, all right? When they ask you to state, all right, stating means there is no need for calculation at all. It is basically question, or rather the answers can basically be obtained directly from the question itself, all right, without calculation, or based on conceptual knowledge, all right? So there is no need for calculation. So in this case, usually the answer will be pretty straightforward. So you can straight away just put 0, okay, as the answer, okay? C, calculate the work done against friction. This is the second time, right? Work done against friction. So we're talking about work done against friction is friction or frictional force multiplied by distance moved where there is this friction acting. Okay, so what's the frictional force? 5. So it applies through the 3 meters, right? So answer is 15 Joule. So out of this 36 Joule of work that I've done, 15 Joule, about slightly less than half, is used to overcome friction. Okay, so again, friction will produce thermal energy. So this 36 Joule of work that I've done, about 15 Joule is actually converted to thermal energy. Question 5, a container is lifted vertically with a force of 10,000 Newton from the WAF, okay, onto the deck of a ship of height 5 meters. So calculate the work done by the crane. Very, very straightforward also. Okay, work done equals to force times distance. So the force, of course, will be equals to the weight of the container, right? 10,000 multiplied by the distance. So they already told you the container has to be lifted up 5 meters. That is the work done by the crane. Okay. 6. The diagram shows a small car of mass 500 kg approaching a hill. It moves up the hill with uniform speed. Okay, it moves up the hill with a uniform speed. Ignore friction and take the value of G to be 10. Okay, how much work is done in moving the car up the hill? Okay, ignore friction and take the value of G to be 10. Okay, how much work is done in moving the car up the hill? All right, so let's highlight. Mass is 500 kg. All right, I have 200 meters here, I have 10 meters here, G. Okay, work done moving up the hill. So we are not given any forces, but we are given a mass. So what can a mass tell us? The mass actually can help us find the weight. Am I right? And that's the purpose of giving us the G field strength, right? So it's 500 multiplied by 10. I have 5,000 Newton. Now ask yourself, what is the direction of force, or rather this weight that is acting on the car? Downwards, right? So if the weight is acting downwards, what is the upward force that is needed to be applied by the engine to move the car up the slope? All right, minimally the car must also act upwards in the direction of 5,000 Newton, right? With a quantity of a magnitude of 5,000 Newton. The car, of course, will also need some horizontal forces, but we are not looking at that. Okay, we are not looking at that. We are looking at just the vertical component, right? So the question is asking how much work is done in moving the car up the hill. Okay, so we already have the weight. Okay, so in this case, what is the value? The work done will be, weight is 5,000, right? So do we multiply by 200 meter or 10 meter? Which one? This is the one, because this is the same, this is the vertical one. All right, upwards, the engine will have to apply upward force of 5,000 Newton. Okay, so work done equals to force times, I know, weight, work done. So what is the force? Force is 5,000, distance is 10, so it's 50,000 joule. So the car has done 50,000 joule of work moving the car up the hill. Okay. Question 7. In a white water canoe course, water flows from a lake through the course and into a reservoir. So water is pumped back into the lake using 5 large pumps as shown in a diagram. Okay, so let's see. So this is the lake. I'm going to assume your canoe will probably start here. Then you kayak down the stream. Okay, so the water will flow, right? Then probably it will stop somewhere here, or it will go back into the reservoir. Then it will stop here and park. But the water will eventually be pumped up using the 5 pumps from the reservoir back into the lake. Or else, the lake will eventually be empty, right? Because the lake is at a higher ground, the reservoir is at a lower ground. Water will always flow downwards. So in order for the water to be sent up, there must be an external pump that helps to pump the water up. So work must be done on the water. Okay, so hopefully you understand this simple diagram. So the volume of water pumped per minute, 60 seconds from the reservoir to the lake is 780 cubic meters whole. They gave you volume now. Okay, volume. So the water is raised through a vertical height. Height is 5.5 meters. Water has a density, and they give you density. I don't know if any one of you already realize there is another topic introduced here. Calculate the mass of water pumped per minute into the lake. How do I find mass of water? I'm given the volume, I'm given the density. What is the formula? I hope you find this familiar. Okay, mass is equals to rho times V. Density is 1000, V is 780. Make sure they tally on the unit. Okay, in this case they do. So it's 780,000 kg. Every minute, almost 1,000,000 kg of water is pumped up from the reservoir to the lake. All right, 780,000 kg. The weight of water pumped per minute. So you already found the mass. They want you to find the weight. Weight equals to mg, right? Okay, let me write it out first. All right, keep the habit. Mg equals to 780,000 multiplied by 10. So in this case it is 7.8 million Newton. Okay. So the total work done per minute by all the 5 pumps. So what is work done? Work done is equals to, in this case is force times distance, right? So force, I need to exert 7.8 million Newton across 5 pumps. So since the question says for 5 pumps, then we don't have to worry about, oh, is it 1 or 5? Just look at all 5. So it will be 7.8 million multiplied by distance, right? What's the distance? 5.50. This is a huge number. Alright, times 5.5. So answer is actually 42,900,000 joule. Okay, be very, very prepared that, you know, for such questions, they can straight away ask you, you know, express your answer in terms of megajoule. So just sidetrack a little. Should the question ask you to express in megajoule, 1 megajoule is 1 million, right? So since I have 42.9 million joule, so this can also be expressed in terms of 42.9 megajoule. Okay? We'll talk more about conversion, all right, when we do our revision. Question 8. An archer fires an arrow vertically upwards into the air as shown in the diagram. So the string of the bow is put back a distance of 60 cm using an average force of 125 Newton. Pull back 60 cm, 125 Newton. Arrow has a mass of 0.18 kg. Energy transferred to the arrow when the string is released is 75% of the energy stored in the bow. Oh, okay. So remember, not all the energy that you use that is contained in the bow after you stretch it is being transferred to the arrow. Only 75% is, all right. So the other 25 probably is lost, you know, through the vibration of the bow itself, etc., etc. Okay. G field strength 10. They want you to ignore effects of friction. Okay, calculate the work done in pulling back the string of the bow. Work done. Showing formula: force times distance. What is the force needed to pull it back? They say 125. What is the distance? They told you 60.0 cm. Please change it to SI unit, okay? Because in this case, the work done has a SI unit of joule. Unlike your moment, all right, it's just Newton meter, Newton cm, Newton millimeter. It doesn't matter. But for joule, it matters. It has to be strictly Newton multiplied by meters. So I'm going to convert it. So it's 125 times 0.6. Answer is 75 joule. Okay. The speed with which the arrow leaves the bow. All right. So you see, EK is equals to half mv squared. We must establish this formula first. All right. But is all this 75 joule being transferred to the arrow? No, they say only 75%. So it's 75% of this 75 joule. So energy in bow, let's do it one step by one step, okay? Oh, not in bow, in arrow. All right, 75% is 0.75, right? Okay, or you just use 75 over 100, doesn't matter. All right, multiply by 75. So how much energy is in the arrow actually? 0.75 times 75, answer is actually 56.25. Do I do any rounding off here? Please do not. This is not your final answer. This is just an intermediate answer. So do not tamper with this value, all right? Just leave it as it is. So how do I find V? Use the formula above, EK equals half mv squared, find V. All right, so remember that time we do the manipulation, 2EK over m square root. Like I said, I'm going to encourage all of you to manipulate the formula. All right, algebraic manipulation should be something that you need to be good at. But should you still feel uncomfortable, of course, you can still do it step by step. It doesn't matter. Okay, so let's put everything into the formula. 56.25 over 0.18 square root. 56.25 times 2 divided by 0.18. Okay, 625. No wonder I find the number so familiar. 25 meters per second. All right, that will be the speed of the arrow, the velocity of the arrow as it leaves the bow. Okay, really fast, definitely can pierce. The maximum height reached by the arrow. So how, you see the arrow is being shot up, right? Oh, okay, the arrow is being shot up. So the thing is, as it shoots up, the arrow will definitely gain GPE. But at the same time, the arrow will move faster or move slower. It must move slower, right? Imagine you shoot the arrow up and then it doesn't slow down. Every time you shoot something into the air, you will eventually reach the space. Am I right? So it has to slow down because gravity is pulling it down. It has to accelerate downwards, right? So in this case, all right, according to the principle of conservation of energy, which we have practiced a lot in the previous assignment, okay, we know that the gain in GPE, no, the change in GPE must be equal to the change in KE. Agree? Okay, so in this case, it's gain in GPE equals to loss in KE, right? So then remember, mgh equals to half mv square. Cancel, cancel, gh equals to half v square. Right? Remember this part? The question wants you to find h. So let's make h the subject. Half v square over, maybe writing this way is a little more familiar to some of you. Alright, but of course, you can also put it as v square over 2g. It's the same thing. Okay? So, put all the numbers in. Alright, what's v square? 25 square over 2 times 10. Oh, 25 square previously was 625. So, 625 divided by 20. Okay, so I think it's a very nice number, 31.25 meters. Wrote it off, final answer ma. So 31.3 meters. Okay. Hopefully, this is a very good question. All right, I would definitely say that this is a good practice question for you to understand the topic. All right, I guess this is the last question. So this is additional question, optional, but of course I will still encourage all of you to try. Question 9. A marble of mass 0.1 kg is released from rest from the edge of a bowl. So the depth of the bowl is 8 cm. Okay, so the marble effectively lost 8 cm in height as it rolls down the bowl, right? When the sphere reaches the lowest point of the bowl, its velocity is 1. So at the lowest point over here, the marble would have lost a lot of the GPE, right? There's a loss in GPE, and this loss in GPE, technically speaking, should be gained as KE, provided if there is no friction. Okay? So let's see, as the marble rolls down the edge of the bowl to the lowest point, calculate the kinetic energy gained by the marble. So what is the kinetic energy gain? EK equals to half mv square, right? The question say is V is 1, all right? So half times 0.10 times 1.0 square, okay? 1.0 square is still 1, so times half is half. So this is basically 0.050 joule. Okay, this is the kinetic energy of the marble at the base of the bowl. Then straight away, suddenly they ask me to calculate the work done against friction. Out of nowhere, why is the question so abrupt? Okay, there's a reason why this is a difficult question, and there's a reason why this part is actually awarding you 3 marks. Okay, because this question is not scaffolded. All right, you need to think of the intermediate steps on your own. All right, if they're gonna provide you with like a part B and a part C and a part D to break down the question for you, then this question will not be considered as difficult. All right, this question will be very easy. So by doing this, all right, they are asking you to think 2 steps ahead. All right, without the question guiding you. So let's talk about it again. All right, the marble is rolling down the bowl, so the marble must be losing GPE. This marble loss in GPE will probably be converted to KE. But in this case, the question did not say that there is no friction. So there must be work done against friction, right? So we are supposed to find this work done against friction. So let's find out first, how much GPE is lost by the marble as it rolls down to the bottom of the bowl. Okay, GPE equals to mgh, right? So m is 0.10 times 10 times what is the height? So like I said, the height, you need to put it in terms of meters because energy, all right, SI unit is joule. We need to calculate in terms of meters. 0.1 times 10 times 0.08, right? 8 cm is 0.08. So this is 0.08 joule. So the marble, as it loses its height, as it drops down the bowl, it actually lost 0.08 joule of energy, but only 0.050 joule of KE has been gained. So where is this difference in 0.030 joule? Energy cannot be destroyed, right? The principle of conservation of energy states that energy cannot be destroyed. So to account for this 0.03 joule of energy, this must be the energy that is used, or rather the work that is done against friction. Right, so 0.080 minus away 0.050 equals to 0.030 joule. So this is the work done against friction. Most likely in the forms of thermal energy and sound energy. Okay, and that's it. All right, that's it for this assignment. So hopefully this last question, I've broken down it simple enough for you to understand. Okay, I would think that all of you should be able to answer this question. All right, as long as you understand this topic well enough. Okay, so that marks the end of this assignment. I'll see you all in the next one.